Adding, subtracting, and multiplying of polynomial functions doesn't create any issues in the domain because those functions, in the arithmetic of them, really you had negative infinity to infinity for the domain of that. However, division always does because division introduces the idea that you can have a division by zero, and that cannot be allowed. Now, rational functions is a function where you have p of x over q of x, where p and q are polynomial functions, or just polynomials. So let's look at this rational function here, lowercase r, and it's actually graphed here on the right, and we're going to ask what is its domain. So really the question is, what are the issues? Of course, polynomials on top and bottom, right? There's no issues in this domain. There's no issues in this domain for both of those. They're just polynomial functions. But the division of the polynomials, that's when we have to ask, well, when does it equal zero in the denominator? Because that is going to create issues. So let's go ahead and factor this. We're actually going to, whenever you're working with polynomials, or I should say rational functions specifically, but polynomials too, factoring is going to be a key thing to do. So let's factor. I'm going to factor the top and bottom, though really we are concerned about the denominator. When does that equal zero? But I'll factor both. So we have on the top, I'm going to take a 10 out of there. That's going to give me, oh, I can also take, no, just a 10. X to the fourth plus 3x squared minus 4. This is a quadratic in form. I could say, for instance, y equals x squared, then y squared equals x to the fourth, and I can rewrite that as y squared plus 3y minus 4. That just allows me to see, well, this is indeed a quadratic. I can factor it using a quadratic in form. So I'm just going to factor this thing. That's going to be y plus 4, y minus 1. I believe, yes. Okay, and y is not what we started with. Y is just x squared. So that means the top factors down into 10 x squared plus 4, x squared minus 1. Of course, x squared minus 1, this is just a difference of two squares, so I can factor it one step further. X minus 1, x plus 1. Okay, so that's the top, the numerator factor. Let's factor the denominator. So first off, x squared plus 4, that's a sum of two squares. That cannot factor over real numbers. You have to use complex numbers to factor it. And we're graphing on the real number plane, so there's really no reason to factor it. It's not going to contribute any zeros. Now the rest of it I can factor. We have 15x cubed plus 15x squared minus 135x minus 135. I don't need to do any kind of fancy looking for zeros for this thing. I can actually just use factoring by grouping. Look at the first two terms. I can take out 15x squared. That leaves me with x plus 3. No, x plus 1. Then look at the next two terms. I can take out a negative 135. Leaves you again with x plus 1. So okay, factoring that out, we get 15x squared minus 135, x plus 1. Of course, the 15x squared minus 135, I can take a 15 out of top and bottom. I'm going to do that over here. That's going to give me 15, or sorry, just out of the first and second term, not top and bottom. 15x squared minus, how many times does 15 go to 135? 9 times. X plus 1. And this is a difference of two squares. I can factor that into x plus 3, x minus 3, and x plus 1. Okay, so this is our denominator. We, of course, also have the x squared plus 4 in it. So I can rewrite r of x as in this form. So r of x equals, Okay, so this is what we get for our rational function. Now, there are things that we can cancel, but before we cancel anything, we must ask when is it equal to 0, because those are the issues in the domain. It equals 0 when we have -3 from this portion, 3 from that one, and -1. Of course, this one is only 0 when x is, I think, 2i and -2i, but those can never happen on the real plane. The Cartesian coordinate system does not allow for those numbers, so we don't have to worry about them. After this point, we can cancel things, of course. We can reduce the x plus 1s, the x squared plus 4s go away, and we can reduce the 10 to 2, the 15 to 3. So it's really just 2x minus 1 on top, and then 3x plus 3, x minus 3 on the bottom. But that's not what the question is. The question is, what's the domain? And the domain then would be everything, the entire real number line, except -3, 3, and -1. Of course, that looks like, you could say x element of r, so all the real numbers, except x does not equal, I'm going to write like this, -1 plus or minus 3. You can also write it as an interval. So that's the domain for this rational function. Okay, give it a try in number 1. Now I should say that you can see here there are these two spots here where the function goes upward to infinity. It was called asymptotes upwards and asymptotes downwards. It does not cross this line here. Or I should say these two lines. Those lines happen at x equals -3 and x equals +3. Of course, there's also another number that we also excluded, and that was x equal to -1, which it looks like is right here. But the way Desmos graphs these, this is from Desmos, it won't actually put holes in there, as what is called holes, and I'll talk about that in a moment. However, if you click on the graph and you hover over -1, it'll actually put a hole in there, and it'll say it's undefined at that point. When you have a canceled factor, like we did here, we canceled x plus 1 and x plus 1. That resulted in this issue in the denominator. So it wouldn't have been an issue if we were just given r of x in its simplified form. But because we were given r of x where x plus 1 and everything was there in the beginning, it was those were here in this original r of x. That means they must be excluded from the domain no matter what canceling we do. The canceled factors, these discontinuities are called holes. They're also called removable discontinuities, because if you were to just put a point right there where the hole is, then you've actually removed the discontinuity. It's now continuous at that spot. Now, of course, for r of x, we said that this was at x equal to -1 because that we canceled that factor right here. And that was the same thing as this hole here that I was talking about. Now, the remaining factors, as you can see, we have this one and this one. Those remain even after the canceling. Those are called asymptotes. And we've seen a number of these so far in different functions, but rational functions really show asymptotes very well. They commonly are there. So keep this in mind. You're going to probably always see these with rational functions. Some of them it won't happen that way, but most of them do. Now, asymptotes have this interesting behavior to the left and to the right of them. A lot of the times you're going to see this flip behavior. So for x equal to -3, that's this vertical line here. You can see that the function on this side is going this way, and then it shoots downward to -infinity. On this side, it goes up to +infinity. And the same thing is true for x equal to 3. On the left-hand side, it goes to negative infinity. On the right-hand side, it goes to positive infinity. It does not cross that line. Once it hits, it gets really, really close to 3 on the left. And then once it hits 3, it's not defined there. And then once it hits, above 3, it's going to be very high in the positive direction. And then it's going to go downward. So you see it jumps there. And that's what an asymptote typically does. Sometimes you'll see asymptotes which will have, some asymptote like this, and then the function will go like this, and then will come down like that. That'll occasionally happen. A lot of times it's like this reverse behavior where it's down towards negative infinity, and then all of a sudden up towards positive infinity. Now, because of this, because it can change depending on the left-hand side and the right-hand side, there's going to be some new notation for it. Now, for our function, as x approached 3, or should say negative 3 from the left, that's what this negative sign is, because on the coordinate system, the left-hand side of the x-axis is the negative numbers. The right-hand side is the positive numbers. So we're going to look at as x approaches negative 3 from the left, as x approaches negative 3 from the right. So this is from the left. This one is from the right. Where does the function go? Where does r of x go? So as it approaches negative 3 from the left-hand side, you can see that the function goes downward. It goes down to negative infinity. As it approaches negative 3 from the right-hand side, the function goes upward to positive infinity. So negative 3 from the left, it goes to negative infinity. It goes down. From the right, it goes to positive infinity. We can ask the same question as x approaches positive 3 from the left and right. Positive 3 from the left, it goes down to negative infinity. And then positive 3 from the right, it goes up to positive infinity. So you're always approaching the asymptote from the left-hand side and the right-hand side, going towards the asymptote, not always going left to right as you would for in behavior. You're looking at it as it goes to the left, it goes from the left-hand side, and then from the right-hand side, going towards this x equals 3. This is called limiting behavior, and this is very important for calculus concepts. So we said this was negative infinity, and this was positive infinity. Okay, try this out in number 2. Now, we've talked about these asymptotes and these discontinuities as wholes or removable discontinuities. But a rational function can actually have, because an asymptote was a vertical asymptote, they can also have horizontal asymptotes. And I should say specifically, it can have one horizontal asymptote, not asymptotes. And that all depends upon the degree of the numerator and the denominator. So look at the numerator and denominator for our function. Like for instance, for us, the highest power of x here was 4 on top. And on bottom here, you'd have to multiply these two things together, but you don't actually need to do that, because if you multiply the highest powers in each factor, that'll give you the highest power overall. Here we have x squared and x cubed. X squared times x cubed is x to the 5th. So that's the degree on the bottom. This is the degree on top for our function. But in general, it all depends upon how the interactions between the two happen. So if the degree on top, m, is the degree of the numerator, and n is the degree of the denominator. If m is greater than n, then we do not have a horizontal asymptote. So horizontal asymptote. If m equals n, then y equal to a over b is the horizontal asymptote, and a is the leading coefficient in the numerator, b is the leading coefficient in the denominator. So you have to take this ratio between these two numbers, and y equal to that number, it'll always be a number, is going to be the horizontal line that the rational function asymptotes to as x goes to negative infinity and positive infinity. And of course, if m is less than n, then y equal to 0 is the horizontal asymptote. You don't need to look at a ratio of anything. So for us, we had m equal to 4 and n equal to 5 in R of x. So this means that y equal to 0 is the horizontal asymptote. And really what this means is that, I'll show you this on the graph above, but as x goes to negative infinity, R of x goes to 0. The 0 is the horizontal asymptote. That means it goes there as you go way out in the positive and negative direction. As x goes to positive infinity, R of x goes to 0 as well. That's what that means. So in our graph, this is R of x here. Let me clean it up a little bit. And you can see as x goes to positive and negative infinity, as x goes this way, as x goes this way, the function gets closer and closer and closer and closer to 0. Closer and closer and closer and closer to 0 on both sides. A flattened line. Now, if this horizontal asymptote was like up here, for instance, then the function would look something like, it would go something like this, and then it would go something like this, or in some fashion it'll do that, whatever it looks like. That's in the case of the degree in the numerator and the denominator being equal. If there's no horizontal asymptote, of course there will be none. It won't do this to a horizontal line. It'll actually do something different, which we'll talk about in a moment. But that's the horizontal asymptotes for rational functions. It will always have one unless the degree is bigger on top, and then it'll have a different type of asymptote. So what are the horizontal asymptotes of these two? Well, the only thing we cared about was the degree, right? So what's the degree on the numerator? Take the largest power of x and multiply them from each term. So here it's going to be x, here it's going to be x, and then here it's going to be x. So we'll go x times x times x. That's x cubed on top. On bottom, we also have a degree of x cubed, or I should say the leading term is x cubed, so we have a degree of 3 over 3. That means that we must look at a over b, where a and b are the leading coefficients. Okay, how do we find that? Well, all we have to do is multiply the terms now that are together. So we have negative x times 2x times 2x. So negative x times 2x times 2x is negative 4x cubed. Okay, and in the bottom we have 3x cubed. So I'll write it like this: a then equals negative 4, b equals 3. Those are the leading terms. This is from the numerator, and the denominator has a leading coefficient, I should say, of 3. So y equal to negative 4 over 3 is the horizontal asymptote. Okay, for the next one, we have the degree on top is 3. I could say m equal to 3 like I did before. M equal to 3, n equal to 3. And on bottom, we have n equal to 2. Here, m is greater than n. That means it has no horizontal asymptote. Okay, and let me show you this. So I've graphed these functions in Desmos. S of x was this first one. it should have a horizontal asymptote at y equal to -4/3. Here's the graph. Okay, I had to play around with the scaling of this thing, of the x and y axis, so that you can see it a little bit better. We also found that the horizontal asymptote was y equal to -4/3. Put that in black. It's a dotted line here. And if I zoom in on it, you can see that the function does asymptote to it. It's hard to see a little bit because it actually crosses it. And that's one of the big ideas here, is that horizontal asymptotes, the function can cross. Vertical asymptotes, the function will never cross. But horizontal ones, they can. It actually crosses it right there. It doesn't really matter. But if we go down past it, it actually goes down a little bit, and it looks like it keeps going, but it actually comes back up to it, and it gets closer and closer to it. The distance is getting less there. And if we go to the other side, the function just asymptotes to that spot. It never goes any lower to it. It will take forever to get closer and closer to it, but it'll never actually get there. Whereas this side, it did cross it, but it would, after that, it'll take forever and it'll get closer and closer to it again. That's the key thing to remember with horizontal asymptotes, is that the end behavior always goes towards -4/3. Okay, for the next one, we have t of x, and there was no horizontal asymptote. So we should see that when we graph it. As you can see, this line keeps going downward towards -infinity. It'll actually keep going that direction. And then on this side, it keeps going upward towards +infinity. It doesn't asymptote to any horizontal line. It doesn't go to any place. This one goes to +infinity on the right, and then -infinity on the left. Now, rational functions that don't have horizontal asymptotes may have slant asymptotes. And the condition, of course, is m greater than n, and m equals n plus 1. It's found by doing the polynomial division. So, what are all the asymptotes of this rational function? Well, to find the asymptotes, we have to factor everything, of course. We have here m is equal to 3, and n equals 2, so we know it has a slant asymptote. It looks like it also has vertical ones, but we'll have to factor that and see. So first off, let's actually go ahead and do the polynomial division. Okay, divide the first two terms, 4x cubed over x squared equals 4x, and distribute it in. That's going to give us 4x cubed minus 12x squared plus 4x, and subtract. 0 plus 15x squared minus 16x. Bring in the next term, plus 15. And then redo the division. So 15x squared divided by x squared is just 15. So we get plus 15. Distribute into there, and we get 15x squared minus 45x plus 15, and subtract 0. It's going to be plus 45, so minus 16 is going to be 29, x. And then this is going to be 0 again. So the remainder doesn't really matter. What matters is this portion here. 4x plus 15, that is the slant asymptote. That means the function will get closer and closer to this line. Of course, it's a linear function. So it's going to be some, this is an increasing linear function since it's positive 4 for the slope. The rational function is going to get closer and closer to that linear function as x goes to positive infinity and as x goes to negative infinity. Okay, let's find the domain. We do that by factoring the denominator. This is a quadratic. It doesn't look to be easily factored. So let's go ahead and first off, let's check the discriminant to see if it's complex. Complex zeros. So the discriminant is going to be the thing underneath the square root in the quadratic formula, which is b squared minus 4ac. B squared is 9 minus 4 times a times c. A and c are both 1, so 9 minus 4 is 5. That's a positive number. That means it does have two real zeros. So let's use the quadratic formula. Negative b, so it's going to be positive 3, plus or minus the discriminant, which we just found is 5, all over 2 times a. A is 1 here, so we get 2. And that's really all there is to it. It's just this this radical 3 plus or minus root 5 over 2. I can't simplify that at all. And so those x cannot equal. So those are the only issues in the domain. Now, the range is going to be a little bit harder to see because we need to look at the graph because of how the asymptote is. I would expect, and this is just my expectations for the domain, would be negative infinity up to 3 minus root 5 over 2, union with 3 minus root 5 over 2, up to 3 plus root 5 over 2, 3 plus root 5 over 2 to infinity. So I would expect that that's the domain, of course. The range, I would guess, is negative infinity to infinity because this rational function goes up to positive infinity and it goes down to positive infinity. However, there could be some kind of gap in there, and let's actually see that by graphing it. So this one graphed looks like this. As you can see, we've got two asymptotes here, and it looks like, once again, a slant asymptote like the previous one I showed you. Looks like there's actually a line here like this. Well, there is that line there, right? We found it was 4x plus 15. So let's graph that. Make it a dotted line. And you can see the function does go towards that line. And then on the left-hand side, it's closer and closer to it. And once again, it does cross this asymptote here. It crosses right there. But that doesn't really matter. What matters is as the end behavior. And then, of course, we also have these two issues. Those are not removable because the top doesn't look like it can factor down into either of these. Let's go ahead and show that here. And so here I've just graphed these two zeros in the denominator as horizontal or vertical lines, and I've dotted them. They're in the green here. And as I go up, it asymptotes to that one. The same thing with this one. On this side, it asymptotes to it. And then go down, asymptotes both of them. And yes, the domain is everything except for these two spots. This is 3 minus root 5 over 2. This one here is 3 plus root 5 over 2. And the range is everything. This goes down to negative infinity, and it goes up to positive infinity. That portion right there covers everything in the range. This also goes down to negative infinity. That goes up to positive infinity. So that, yeah, the range is definitely everything. There's a y value. This function will hit every y value. at some point. So there you go. Give it a try in number 3. Now, if m equals n plus 2, so if it was m equaled n plus 1, that was a slant asymptote or a linear asymptote of some kind. If it's m plus 2, that means the top degree is 2 greater. And when you do the division, you're going to see you're going to get a quadratic as your answer. So this gives us a quadratic asymptote. And likewise, if it's 3 more, then you have a cubic asymptote, because when you do the division, you're going to have an answer that is cubic, x to the 3rd power of some fashion. So the same pattern continues, 4, you're going to get x to the 4th power and so on. And it always kind of fits this kind of idea where you have, this one was a line, but if it's quadratic, it's going to be a parabola eventually. And that's how the horizontal or slant or quadratic cubic, that's how that always works. It always affects the end behavior. Let's look at an application of this. A drug's concentration in a person's bloodstream can be modeled using this, and it's a rational function. So C of t is the concentration in milligrams per liter, and t, of course, is the time. It'll be in hours after the drug is injected. So what are the asymptotes? Well, we know we have horizontal asymptotes. If this thing equals 0, well, 3 plus t squared equals 0 when you subtract 3, take the square root, and of course that's a complex number. So therefore it has no no vertical asymptotes, because it can't, the complex number can't be shown on the graph. Now it can, however, have a horizontal asymptote, and in fact it does, right? M here is 1, the degree on top, and the degree on bottom is 2. 1 is smaller than 2, right? So that means y equal to 0 is the horizontal asymptote. Just look back at that table that I made. So we know that eventually this function, as t goes off to infinity, the horizontal asymptote will get smaller and smaller and smaller, and it'll go to 0. So let's go ahead and see what is C of 3, C of 72, and C of 168. So after 3 hours, 72 hours, and then 168 hours. If you go back to the function, it's going to be, I'll just write it down here, 3 plus t squared. So C of 3 is 2 times 3, 3 plus 3 squared. 6 over 9 plus 3 is 12. It's going to be 1/2. And it said that this was in milligrams per liter. It must be liter of blood, right? Since it's in the bloodstream. So there's 1/2 milligram per liter of blood. Then after 72 hours, it's going to be, use a calculator for this, 144 over 5187, or approximately 0.03 milligrams, right? Milligrams per liter of blood, so even less. And finally, C of 168, I'm just going to use a calculator for this. I get approximately 0.01. And as you can see, this is 0.5, 0.03, 0.01. This is getting closer and closer to 0, which is what we expect from the horizontal asymptote. Now, what I recommend you do is you actually graph this thing on your own and see how it goes towards this y equals to 0 horizontal asymptote. I should also make a note, because this is a real scenario, that t less than 0 doesn't make sense. So there's really no reason to look on the left-hand side of the graph, because none of that really matters. That's backwards in time, and this is not really defined in that portion. So that's not the thing to always keep in mind, is how does the real world scenario affect the actual domain of the function.